Okay, I got the camera on now. So what we have is we have a cart. That looks like a slope, but it's level. Level surface, we got a cart, car, whatever. And we've got a rubber band. RB for rubber band. Length of 20 centimeters. Tension. Six newtons. Okay? Now, when the length is 8 centimeters, the tension is 0. So when the car is here, it will have traveled 12 centimeters with an average tension of 3 newtons. Well, that tension does work, force multiplied by the displacement. That would be an average of 3 newtons times 8 centimeters times 12 centimeters, sorry. Length is 20 centimeters, length is 8 centimeters, traveled 12 centimeters. That's 36 newtons times centimeters. But the standard unit is joules. Centimeter is 100th of a meter, so 36 newtons times centimeters is 36 newtons times 100th of a meter, which is 0.36 joules. And that's from 0.36 newton meters, or 0.36 newton meters squared per second squared. Because, of course, a newton's a meter per second squared. A kilogram times a meter per second squared. Okay? Second law, force times mass. Mass times acceleration. Okay. So the work is 36 joules. If you were to integrate the force, of course it's a simple linear function, if you get the equation of the function and integrate from 8 centimeters to 20 centimeters, you're going to get 0.36 joules. Okay? Easy to integrate. Just find the antiderivative. Calculus class, I don't know if you've got the introduction to integration yet, but that's probably coming up soon. And it's just an antiderivative. Okay? If it's 1/2 x plus 8, which gives you force in newtons if x is in centimeters, because of the way these units are, then your antiderivative, what's the antiderivative? What do you take a derivative of to get 1/2 x? Well, if you're going to take a derivative of something and get an x, you're going to have an x squared, right? But x squared gives you 2x, and if you want to get 1/2 x, you'd better take the derivative of 1/4 x squared. And then it's plus 8 times x. There's your antiderivative. You evaluate it at x equals this position and this position. I'll leave it to you to do it from position 8 to position 20. You get the same thing. So it's a simple integral, but we're not going to use the integral right now. We'll just use the average force. Okay. But the average force, well, is equal average force times displacement. An integral over an interval. The integral of function over an interval is just the average of the value of the function, average value of the function times the length of the interval. It's a basic fact in calculus, probably not until second semester, but we're going to use it. Okay, so we don't have to do the integrals yet. Now, kinetic energy, 1/2 mv squared. Work done by the net force is a change in kinetic energy. That's your work energy theorem. So question, what's a change in kinetic energy from release to rest? A lot of discussion, but this thing is released, its velocity is 0. When it comes to rest, its velocity is 0. So kinetic energy, 1/2 mv squared, v is 0, starts at 0, and at the end v is 0, so kinetic energy is 0, so the change in kinetic energy is 0. Okay, what's the work by net forces from release to rest? Well, we got far enough, so far, okay, we got to for the first 12 centimeters, I'll call it mu k, it's actually a rolling friction, but we'll call it a kinetic friction. UK times the normal force. Normal force is equal and opposite to the gravitational force because this thing's level. Plus the force of tension. Now this thing comes to rest after 3 meters. It comes to rest at this point. The last 2.88 meters. F net is negative mu k mg. What's the total work? It's 0. What else is the total work?
Terrible. Okay, just suck it up. Yeah, just suck it up.
It's the work done in the first 12 centimeters, which is this, plus the work done in the remaining displacement, which is this. So we've got a like term here, mu k mg times 12 centimeters and a negative mu k mg times 288 centimeters. So we just add the two displacements and we get 3 meters, right? I've got FT, should be FT average. Okay? So we've got this. We know the mass, we know G. We easily solve from UK, can't we? So work that out for next time. And see if you can answer the remaining questions. Our context in this chapter is energy conservation, etc. But this problem combines stuff you learned in previous chapters about tension, friction, work against friction now. So it's fairly complex, but you should be well equipped to put all this together.